First thing today is you want to make sure that you know that all the stuff I talk about today is on the UO Lab webpage, and it is under other links. And if you kind of hover here, this menu appears, and then you can go under statistics. You don't have to be on Pale Moon to go to the UO Lab webpage just to control the experiment. So you can go anywhere but on control to get stuff. So UO Lab, other links, statistics. When you click there, everything we are going to do is under regression analysis here. I'm going to open up this PowerPoint. Everything I talk about is also summarized in that Word document that you see here. We're also going to use the Excel data that you see here. I'm going to walk through an example so you can see what I'm doing. And then we're also going to do this linear analysis VBA tool by Dr. Baxter, which is another Excel document. And I'll review that when we get a little closer to using them. But just note that everything we talk about today is under this lab page, this UO Lab webpage that's under other links, statistics. Okay. We're going to start today. I don't want to make this full screen. I think it's going to mess it up. Let's see what happens. What do you guys see now? Is it too small for you guys to see, or can you still see this?
No, looks good. Looks
okay.
Good.
Yeah,
Let's talk about regression for a minute. What good is regression? We actually use it all the time in engineering. We use it to analyze data like you're doing for your airflow experiment. You've got theory, and then you want to fit it to some data, and you're specifically getting a discharge coefficient, so the slope. We often do it for data reduction. So if you remember way back, we actually did this a little in 285. I think you might be doing this, or 385. You might be doing this in 445 soon with an ebuliometer data, where you take VLE XY data, PXYT data, and then you fit it to a model like Margulies or NRTL or whatever your favorite activity coefficient model is. We do that so we don't have to store all of the PXY data. We just need to store the parameters in a table for different binary mixtures. So that's what we mean by data reduction, or Antoine equations, right? Antoine equations, another example where we don't want to store tables and tables of vapor pressure data that then you'd have to interpolate through. We want to create an equation where you just have to store a bunch of constants. And so there you get some examples of why we use regression. Now, when we talk about regression, there's two general classes. There's linear and nonlinear. And linear and nonlinear does not refer to the functional form of the equation we're using. It refers to the coefficients, linear in the parameters. So a straight line, of course, is linear, but there's a lot of other linear things that have linear parameters, or models that have linear parameters. Here's just a couple examples. So look at these, and you tell me, spend a second going through these, which one of these are linear in the coefficients and which ones are nonlinear? Because we're only going to talk about linear regression right now. Nonlinear will come later in the semester. So someone here in a minute, tell me, maybe I'll just ask. We'll start with Hannah. And we'll go with number 1, and then Adam will be number 2. Hannah, is number 1 linear in the parameters?
In the parameters, yes, but in
yes.
the function itself, no.
Good. Even though it's a polynomial, and you think that's not a linear equation, it is linear in the parameters. And so everything we talk about today is you can get the parameters using linear regression. So the A, B, and C, it really means that there is one coefficient in each term, and the coefficient's in the front of the term. It's not inside a cosine or a sine or an exponential or something like that. So Adam, tell me about this one, number 2.
So number 2 would not be linear because we have the b parameter in the exponent.
Yeah, so yes. Now, this is the trick question. What can I do to make this linear?
I take the log of it.
Yeah, take the log of both sides. Then if I'm fitting log y versus x, then I'd have a slope of b and an intercept of log A. So I can make this one linear. Now that's not the best thing to do, but it's done all the time. It actually kind of biases some of your errors, and we'll talk more about that when we talk about nonlinear regression. But for today, you can linearize it and use linear regression tools. Okay, who's up? Josh, are you there? What about number 3?
I guess it's linear.
Yes, it is linear. This is an equation we use in Dipper all the time to fit second virial coefficient data. But again, it is one parameter in each term, and then it's in front of the term essentially. Okay, Nate, what about number 4?
Which Nate?
You, Nate Green was.
I'm thinking nonlinear.
Can I make it linear?
Yes.
I can't. I mean, well, why? What term is the messed up? Is this one right here? Even if I take the log of both sides, this term would be okay, but notice there's still a B and C in one term. So this is the Antoine equation. This is not linear. It's not linear regression. I'd have to use the stuff I'll talk about in a couple weeks. So this one we can't do. Everything else, of course, straight line is linear. And so 1, 2, 3, and 5 can all be done with linear regression. 4 cannot, even if I take the log of both sides. Okay. I'm going to motivate our work with what I call straight line. I'm going to try to say straight line rather than linear, but this is just y equals mx plus b. And when we talk about regression, we often talk about an array of coefficients. So b0, b1, if I had a polynomial, it could be b2, b3, b4, but we just have b0 and b1. So b0 is an intercept, b1 is the slope, and then the difference between my model prediction and the measured y value is the error, or we often call them residuals. And pictorially, that's this, right? The difference between what I measure and my model gives me my error. So those are important concepts we'll return to later. What are my errors? And then I talk about y hat is what my model gives me. It's my predicted y. So y without a hat, that's my measured y data. Y hat is predicted, which is, in this picture, the straight line. Now, you've actually been fitting data for a long, long time, all the way back in 263, maybe earlier in other classes, but I've done this all the time in Excel. I've got some X data, some Y data that I measured, and I want to fit it to a straight line. I could put a slope and an intercept into 2 different cells. I could then use that. I could guess 1 and 1 if I wanted to. I could guess 1 and 1, use that slope and intercept cell to create a predicted Y value. I would then get my errors, and maybe I squared them in here, but eventually I'd get the sum squared error. And the sum squared error is something you've seen before. You use solver, reduce it to 0 or minimize it, and then by changing the slope and the intercept. So the sum squared error, let me see if I can bring this down. You can't quite see everything, right? The sum squared error is an important statistical parameter. It's related to the mean squared error. The mean squared error is related to the sum squared error. Notice that sum squared error divided by some number, which is related to the number of independent, the degrees of freedom. It's n-2 because we predicted a slope and an intercept, 2 parameters. If it was a quadratic, it would be n-3. But just remember that the mean squared error is related to the sum squared error. It's kind of like an average sum squared error. Okay. Now, so you've been doing this and you're saying, why are we having this lecture then? I know how to get slopes and intercepts. I can use Excel. I can use solver. I could fit it to a straight line like with a graph. I could use Python. So what we have to answer now is how good the fit is and what are the errors involved. And to answer how good the fit is, I want to talk about the R-squared statistic. This is a useful statistic, but it doesn't tell you everything. It tells you how well the data fit the model, but it doesn't tell you if the model's correct. We'll explain a little more about that in a second. I just put these here. There's actually equations that you can use to calculate R-squared, and they're not that complex. Let's just go through what this equation means. it means I'm going to look at my predicted y value from my equation, that's the y hat, minus the average y value for every single value I have, square that, and then sum them up. Then I'm going to compare that to the actual measured y value, subtract from the average y value, square that, and sum it up. And the ratio of those two is what I call r squared. Now, why doesn't r squared tell me everything? Here are 4 different data sets fit to the exact same straight line model. So you can notice I have a slope of 0.5 and intercept of 3. Slope of 0.5, intercept close to 3. All through here, I have the same r squared values, 0.667, close to 0.667. But I think you can see that r squared doesn't tell me the whole picture here of how well this model fit the data. What is the problem with fitting a straight line here? We don't like it, right? It's got curvature. And so how am I going to tell whether, up here I'm thinking, oh, this is okay, right? The data are kind of random, they're scattered about, and I kind of like that. This looks like something's wrong. This could be an outlier, or maybe I really do have a delta function there. I don't know, but I definitely have some problem here with my model or my data. And so what else do I need besides r squared to tell me if I have a good model? That's where I want to look at the distribution of the residuals or the errors. So I've just picked 2 of the figures we saw on the last page, and I plotted the residuals or the errors. And what you want to see is something like this. The errors should be random. You shouldn't see a pattern in them. And they should be scattered about 0. You actually forced it to scatter about 0 when you did your solver and reduce the errors. So we hope that's true. But you want them to look like this. You don't want there to be a pattern. If there's a pattern, it means there's something that my model doesn't capture in my data. In this case, maybe the data's wrong because I got this outlier, but there's definitely a pattern here. Let's look at the other 2 examples. This one looks okay, right? It's kind of randomly scattered. This one definitely has a pattern. And this is often what you see if you try to fit a straight line to something that has curvature. You see this all the time when that happens. I do not want to see this. It means that my model is not capturing something of my data. So take home message here. There's 2 things you want to check to see if your data fit the model well. R squared wants to be high, ideally close to 1.99, 0.98. And then I want to have my residuals random about 0. Okay, any questions on that so far? Well, let's take a little second then and look at these 2 for a second. Look at this design of experiment. Let's say I was trying to fit data across this response versus this one. What do I not like about this design of experiment? Where I've taken lots of data at one end and only one point at the other.
It seems like you're only really testing one condition of your whatever experiment you're doing.
And why would that be problematic?
Well, because if you want to be able to describe the behavior of whatever it is you're measuring over a range of things, you actually have to measure it over a range of things. You can't just do one end and then the other. You kind of want to look at the middle as well, because things can behave differently at intermediate points than they do versus the ends.
Yeah, if I don't know, if I haven't taken any data, how do I know there's not curvature in this data? So that's definitely a huge, huge issue. I have to know that it should be straight. Now, let's assume this is actually not too bad of a design of experiment if you know the data are straight. But I would also want to maybe do 5 over here and 5 over here. I would never just want to do 1. And the reason I don't want to do 1 is because if I had some error in this point, then it's going to shift that slope and intercept a lot. So if I know for sure that my data should be a straight line, then I actually get a good design of experiment by pushing all of my experimental resources to the ends, because then I get the maximum sensitivity of the slope and intercept. But basically for this class, and what you kind of see in the airflow data is we've given you data along the whole response, the whole independent variable, so that you can make sure that it is linear. It should be straight line. Yeah, so take home message here, again, R squared and residuals, you want to put both of those in your report. when you are showing the data. You can leave the R-squareds in captions or in the figure themselves. You're going to want to show the residuals to say, yes, I don't have a pattern here, or something like that. Okay, what are the other questions we ask? There's two other big questions. One of them is, once I fit my data, what's the error on my slope and intercept? If I say my CD value that you get from airflow is 0.9, is it 0.9 plus or minus 1, plus or minus 0.1, 0.1, what is it? And then the second thing I want to ask is, if I use my model to predict now, how accurate is that prediction? Take the Antoine equation for a second. If I have vapor pressure data at 300 Kelvin and 350 Kelvin, and I fit that, how accurate is my prediction at 325 Kelvin, where I didn't have data? Those are the two questions I want to ask. How accurate are my parameters, and how accurate is my prediction? Okay. What we're going to do here is go through several pictures that have a bunch of lines. And I'm going to refer to them as the inside lines and the inside bands and the outside bands. This is the same data we looked at from that first example. Got a straight line, that's my model. I have these green inside bands, and I have red outside bands. Now, down here we say the green is called a confidence interval and the red is a prediction band. The problem with the literature is that sometimes they swap these two. Their statisticians are not consistent on their nomenclature. So I always refer to them as the inside bands and the outside bands. And what I care is that you know what they mean. I won't test you on nomenclature, but you know what they mean. The inside bands tell me how accurate my prediction is. Or it's like a 95% confidence interval we talked about last time. So if I predict, say, at 9, and I go up to where my prediction is, the error on this value, which is something like, what, 6? Then my error is actually between these green bands at 9. So it's about plus or minus 1. So about between 7 and down to 5. So that's what the inside bands tell me. It tells me my error on my prediction. So at 9, I'd go up my equation of 3 plus 0.5x gives me something like 6. And then it's plus or minus 1. Now, what do the outside bands tell me? The outside bands tell me, if I did this experiment again, and I took a bunch of data between about 4 and 14, let's say I took 100 data points, 95 of them should be between these two bands, and maybe 5 of them would be outside. So it's like my 2 sigma. Right? Sigma tells me if I do the experiment again, where do I expect the data to be found? Confidence intervals tell me how accurate I know the mean, in this case, the mean response or my model. So let's see if I explain the last 2 days of stats well. Someone tell me, if I took 100 more data points, what would you expect to happen to the green bands, and what would you expect to happen to the red bands? Who thinks
they'd get more tight?
Which ones?
Let's see. The green bands would get more tight, and then the red bands might get a little bit wider.
Yes. So basically, the red bands would stay about the same because they're like 2 sigma, right? It doesn't matter how much data I take. They just kind of hone in on the correct sigma. But as I take more and more data, the green bands would get closer and closer to my model. I'd be more confident in my model. And so let's go through this a little more. Oh, before we do that, you see some equations here. Don't get freaked out on these equations. I'm never going to test you on if you can do these equations, so to speak, because there's tools that calculate all this. But I want to show you that you can calculate errors on the slope and intercept, or on the parameters. And it looks very similar to stuff we saw last time, in the sense that 95% or a 99%, whatever you care about, confidence intervals often look like a standard error, which is denoted by this S, times a t statistic. And this t statistic is the exact same t statistic we talked about last time. So t.inverse.2t, and if I wanted 95, alpha would be 0.05. And I have to remember about the two-tail thing, like 1 minus alpha over 2 that we've kind of talked about. Notice, though, that my degrees of freedom is n minus 2. When we talked about last time, where we had like single measurements, like what's the delta P at 7.2 gallons per minute on our experiment, I was only using 1 degree of freedom to predict an average. Now I'm using 2 degrees of freedom to predict the slope and intercept. If I had a quadratic, it would be n minus 3 or things like that. Point is, though, that you know how to do this. This is t.inverse.2t. So how do I get the standard error? The standard error that we talked about last time was sigma over square root of n. When I fit data, the standard error looks like this. I take all my x data, I square it, and sum it up. I take all my x data, individual points, subtract it from the average of the x data, square that, and sum it up. I got an n here, I got a 0.5 here, and then I have this sigma hat. What's sigma hat? It's actually not that hard. I'm just going to go back here. You can see that was related to the sum squared error. It's actually the square root of the mean squared error. Point is, all this is stuff that if I gave you all the equations and you had enough time, you could calculate all this stuff. It's not magic. It's sum squared errors. It's just looking at squares of the data and ratios of the squares of the data. And then for the intercept, it's very similar. It's a standard error times a t statistic, same t statistic we've always talked about. Now the standard error looks a little different. It doesn't have this sum of x squareds in the top. It just has a 1 in the top. So that's how I get the confidence interval on my slope and intercept, or my other parameters I'll talk about if I did other complex equations. How do I get the inside bands and the outside bands? It's also very similar. It's a standard error times a t statistic, and a standard error. Oh, and then, sorry, what does the standard error look like? The inside bands look like this. Notice I take whatever value I'm trying to predict at. This is not a summation. So if I wanted the error at x equals 9 or x equals 8, right, I'd put an 8 right here. I subtract it from the average of the x data, square that. This is all the sum again. I have that sigma from this mean squared error, but then I multiply it by this t statistic. But you'll notice that these bands are bowed out. Why does it make sense? And remember, these bands represent the error of my prediction. Why does it make sense that I am less confident at the ends or far away from the middle of my data than right here? Why does it make sense?
Doesn't it have something to do with your average? And that you use the average in finding the error?
So mathematically, yes, you're right. This is mathematically, that's why it happens, right? Is I'm seeing how far away I am from my average. But why does that make sense from a physical standpoint? Why would I naturally be less confident here than I am here?
Okay, you have a lot of data points in the middle that can kind of corroborate each other. But the ends, you have a final endpoint and a final starting point. Nothing beyond or before those.
Yeah, I mean, if I look right here, I've got data on either side of me that tell me that this thing's not doing something crazy. Out here, I don't have any data to tell me that this thing doesn't go up or doesn't go down. I'm just naturally less confident further out. Mathematically, like Hannah said, it comes because I'm looking how far away I am from the average of my data. But physically, that's why it makes sense. Where I have less data, I'm less confident. Again, as I take more and more data, these inside bands get closer to the prediction. The outside bands stay about the same because they're like 2 sigma, the expected range of data. If I took more data, where would I expect it to be? Okay. I'm going to go show you now that this really isn't super complex to do. If you had to take the time to do it, you could do it in Excel. So you've got access to this. Remember, it's on the statistics webpage over here under other links, stats, UL Lab webpage. It brings up this page. I'm just looking at this Excel data right here. And I'm going to make this a little bigger so that we can see everything. So I've just got X data and Y data here. You don't need to be worried that these are integers. Nothing special about the integers. I just have X data and Y data. Sorry, give me a second. Here we go. And I'm just going to walk this through similar to what you would do in, say, 263 if you were fitting data. So X data, Y hat is my prediction. So I have to guess a slope and intercept. So I'm just going to guess maybe a slope and an intercept of 1. And do you remember how in Excel you can name cells so you can refer to those in equations? Look up here in the left. I named this one M and this one B. You guys remember that from Excel? You can name cells. So when I type this in, I'm just going to say Y is equal to M times X plus B. I just guessed 1 and 1. And then I'll copy that down. I don't know why it goes beyond my data. Now, if I was doing this in Excel, I now want to get the error between the prediction and the measured data. So Y hat minus Y. Now, you may have squared this right here in 263. I don't want to do that because I want to plot the errors later to make sure they're randomly distributed. But there's a nice function in Excel called sum square. Let me copy it out so you can see it. I'll put it right here. Sum square squares all the values and then sums them up. So that's the function I'm going to use here. Now, if we were doing this in 263, I'm kind of done setting up my MathCAD. Now I want, or my Excel, I want to go to data, I want to go to my solver, and I'm going to minimize. I called this cell sum squared error, SSE, but it's this one right here. I want to minimize it by changing the slope and intercept guesses. And once I solve that out, my sum squared error goes down, and I've got it plotted over here. The dashed line is the Excel trend line to the data, and the red line behind it is my fit that I just graphed right here. So X versus Y. And so there's my slope and intercept. You can see the slope and intercept I get from solver is the same as the slope and the intercept I get from the trend line. So there's 263. Any questions about that? You've been doing stuff like that for a long time. Okay, so now we want to know how accurate are my parameters, so my slope and intercept, and how do I get my prediction bands and my confidence bands? So I need a few things. One of the things I need is Y hat minus Y bar. This is to get R squared. So Y hat minus Y bar. And I have a cell down here called Y bar that just takes the average of all my Ys. Let me just show you that. So Y bar is just the average of all my Y data. Copy that down. And then when I do sum squared of that, that's the top part of my R squared value. The bottom part is Y minus Y hat, or Y bar. So the ratio of these two numbers is R squared. And I put that down here. And you can see that that R squared 0.89 is the same as 0.89 over here. And just to show you how these things are, they're not magic. They come about by looking at the data and how well your model relate to the data or describe the data. Now, the other thing I need to get, if you remember this PowerPoint slide, I need X minus X bar for several of my parameters, errors, and also for my confidence band, X minus X bar, X minus X bar. And then I'm going to sum those up and square them. So here's my X minus X bar. X minus X bar, right? This is all with your measured data. There's nothing predicted here. It happens to be integers just because everything else was integers. My X bar is just the average of my X data. Now, how am I going to get now my errors on my slope and intercept? I need to now go get the sum of all the X squared data, take the square root of that and multiply it by sigma hat. remember sigma hat is related to sum squared error. And so down here, I take my mean squared error, SSE. Let me just copy that out so you can see it. That's what's right here. This is SSE divided by n minus 2. So SSE divided by n minus 2. I need a t value. I'm going to just change this real quick. This is, oh, I should have changed this. This is using the deprecated one, but this is t dot inverse dot 2t gives me my t value. I'll copy this out so you can see what I'm doing. And just remember that 0.05 is my alpha value. Notice that I'm going to move this over just a little bit so you can see it. Count is a function in Excel that just counts all the cells if there's something in them. So I use that to get the number of n I have. It's just count of all these numbers right here. So I had what, like 17 down here on the 17 points, and then I have to subtract off 2 for my degrees of freedom. So this is just my normal t value we talked about last time. And then to get my slope and intercept, I'm going to just do something like this. My slope and intercept, I need the standard error on each of these. And this is what you see here. And let me just go through this equation so you can see how it works. So this does sum squared of B3 to B9. That is this top thing right here. I'm just squaring all the X data, summing it up. I've got an N in the bottom. I've got sum squared of X minus X bar, which is this column. I could have just used this, or this column right here. I take the square root of that, 0.5, and then remember sigma hat is the mean squared error to the 1/2, because mean squared error is actually sigma squared. But if I gave you enough time, you guys would be able to just go through these formulas, and you could do this yourself. Just to show you, here's the one that is the bottom one. It has a 1 on the top rather than a sum of the square of the x's. So then I take my s, I multiply it by t, and that's the error on my slope and intercept. So here's my s times t for each of these. So my slope is actually 0.5 plus or minus, or sorry, my intercept. My intercept is 0.51 plus or minus 1.8. The intercept errors are actually usually big. And so you could see that this is kind of all over the place. My slope error is much more accurate, 0.92 plus or minus 0.17 in this case. Or if I add and subtract those values, that's what you see here. How did I get it to be 95%? Someone tell me, why is this a 95% confidence interval? Where did I set that versus say 99?
That was your alpha value, right?
Yeah, and where does the alpha go in? Right here in my t dot inverse dot 2t. So if I wanted to change this to 99, all I'd have to do is change this to 0.1. And then you see that my errors get a little bigger, and my bands actually over here got a little wider. I'm going to change this back to 0.05.
Wouldn't you change it to 0.01 to get 99?
Yeah, 0.01.
Oh, okay.
That's what I had here. 0.01. I don't know if you can see that, but it is 0.01. Okay. What about the bands? Notice on the right, over here, I still need a standard error times a t statistic. Same t statistic or t number. I just need my standard error. So I need 1 over n. I need to take my instantaneous x value, subtract it from x bar, square that, and then get that stuff here. And so that's what you see right here. 1 over n. Let me copy this out so you can see it. 1 over n, x minus x bar. And so it just references my x value over here in column B, minus x bar, which is down here. Square it. And then I use sum of the x minus x bars. That's this column, sum squared. And then I have take the square root of that, and then I also have my mean squared error to the 0.5 to give me my sigma hat. And then to get my upper and lower, I have to multiply it by my t statistic and then subtract it. So that's just my standard error times t, and then I subtract that from my predicted d, and then I add it to get my bands. And then the outside bands is very similar. I just have a 1 right here that you see in this equation. So what's the take-home message from this section? One, I don't necessarily, you'll never need to memorize these equations. I just want you to know that there's a fairly simple mathematical way to do this. But the bigger thing is, how do you use them? What do the inside bands mean? What do the outside bands mean? And then also, like when you're getting your discharge coefficients here from your data, you can actually tell me how accurate that discharge coefficient is by doing something like this. I can calculate the error on my slope. Now, Dr. Baxter has actually made a tool that does this fairly easily. I don't know why Excel doesn't do this natively. It does, it will give you the error on the slope and the intercept, but it will not give you the prediction bands. But Dr. Baxter's created a VBA tool that will. So we're gonna just walk you through this to show you what happens. Let me zoom in so you can see this. I've got several examples on the sheet. Again, this is all available to you. And you can use this for the quiz, for any data analysis, anything you want. So this is the same data we've just talked about on my example. You have to enable the macros because this is a VBA thing. And then there is one macro in, oh, sorry, wrong. That's not what I want. Macros, here we go. It's called linstat, linear stats. When I run it, it brings up a window. What I want to put in here is my X data, my Y data, and then this defaults to a polynomial. So for a straight line, I want to put a 1 right here, and then I want to include a constant, which is the intercept. So I'm just going to come over here. I'm going to select all my X data. I'm going to select all my Y data. I want first order for a straight line. You don't have to worry about inherent error in this case. I want a 95% confidence interval. You could change that to 99 if you wanted to. This right here is just for graphing purposes. I'm going to graph 20% beyond my data to kind of see how it extrapolates. I hit OK, and it brings it creates several sheets down here at the bottom. And so you see it gives us these inside bands, outside bands plot. So the middle orange line is my model. The inside bands, gray and yellow, are my how accurate my prediction is, or how accurate my prediction is. And then the outside green and blue are, if I did this experiment 100 more times, 95% of the data should be in there. You can see a data summary here. Here's my intercept and slope. So x to the 0, x to the first power. Here's the confidence intervals on those. So my slope or my intercept and slope. This is all just graphing, right? Here's my x data that he's using to graphing, y data that he used to do this graph here. But this does all of the stuff that you need for you. Here's my parameters. Here's my confidence interval on the parameters. There's a couple other things it gives. Here's my distribution of residuals. I want to check that to make sure that my model's good. It's just not R squared, it's R squared plus looking at the residuals. And then there's one other thing here that we haven't quite talked about yet, but I'll go through it now, and you won't necessarily need this right now, but this tells me the likelihood, or where I should put, how likely are different combinations of X and Y. Or I get a confidence interval on my slope and my intercept, but they actually are not independent of each other. I'll never have the highest slope with the highest intercept or the lowest slope with the lowest intercept. This square represents that. So the square represents if I used my 95% confidence interval and added the top, and then for the slope and intercept, I could get a combination, something up here, high, high. I could also get low, low. But that actually is not what happens from statistics. It actually does a range, and that's what you see in this green joint confidence interval. So if I really wanted to know what combination of pairs of slope and intercept I would likely find, what you see is it would be the ones inside of this green band. I won't talk to you too much about that right now for this lab. We'll review that later. The things you want to know now are you're going to want to put a graph in something like this, right? That shows my inside bands and outside bands. You're going to need to be able to get your parameters and your confidence intervals on your parameters. Now, what if I had polynomial? I could run this macro. When I run this one, it's going to say, hey, do you really want to run this? I already see that you have some worksheets here. It's going to delete them. You say, yes, I want to delete those. Polynomial, this polynomial data is, I think, liquid heat capacity data. It fits a polynomial. I'm going to fit it to a cubic polynomial. Actually, a third order polynomial. So I do the same thing. Here's my X data. It's a lot of data here. Here's my Y data. I'm going to fit this to a third order polynomial. I do want to include a constant. I click OK. And this is what it looks like. In this case, this data, there's a lot of it, and it actually fits the model pretty well. And so you can see that my confidence and my prediction bands are about the size of the symbol almost. It's really good data, fits the model really well. Here's where I can get my residuals. Uh-oh, I got a pattern. So it looks like I might be trying to overfit my data. But this is where you have to say, okay, is this a problem? It's actually not too much of a problem with heat capacities. And I say, why? Why is it that I don't care necessarily if I'm overfitting the data for heat capacities? What mathematical operation do we usually use for heat capacities?
We average them a lot.
We average them. So I don't really care if the slopes are right. And what other operation do we do, which is kind of like an averaging? We integrate, right? Whenever you're doing thermo, you integrate your heat capacities to get heat or work or things like that. So integration, we don't necessarily care about slopes. So we really just care about the absolute value. So that's why we don't care too much that we are overfitting liquid heat capacity data. And then you see all these little bands that tell me where my parameters would be. And then where's my last one I want, oh, here's the data summary. Here's all my parameters, x to the 0, x to the first, x to the second, x to the third. And here's the confidence intervals on those parameters. Okay, what about something more complex than a polynomial? What about, I'm going to skip over here. What about this second virial coefficient data we kind of talked about? I have x to the 0, then 1 over x, or x to the -1, x to the -3, x to the -6, x to the -9. How do I fit that data? I can still use this tool. What you have to do is create what I call the x matrix, or it's the functional dependence of your independent variable, of your x data. So here's my x data. This is temperature versus second virial coefficient data, is what this is. So what I want to do is create a column for each one of the independent variables that you see in your model. So x to the 0 is my constants. 1 over x is literally just 1 over x. And then I have 1 over x cubed. And then 1 over x6, 1 over x to the 9th. And then I have my y data. When I run my macro, what I now want to select is that entire x matrix. That's why it actually gives this f of x values. It's just not a column, but this is a whole x matrix. So the first column is x to the 0, next column 1 over x, next column 1 over x cubed, and so on. I do not want to include a constant here. And the reason is because I'm explicitly including a constant by having a column of 1s. And I think the program will actually say, hey, you don't want this checked because you already included column of ones. My Y data is my last column, which is my second virial coefficient data. I'm still doing 95% confidence. And we hit OK. And what you see here is a parity plot. Or this is my measured Y versus my predicted Y. So if I have a great model, which I do here, this should be kind of on the 45-degree line. If my model wasn't predicting well, you'd see some points up here, points up here, or something like that. Here's the residuals. They look pretty good. They're randomly scattered. And here are, this is x to the 0. That's my intercept and my confidence interval on that. 1 over x, 1 over x cubed, 1 over x to the 6th, 1 over x to the 9th. How do you know, let me see if I zoom in a little bit. How do you know that this has to be the 1 over x to the 9th term versus this one? If you look at the magnitudes. Does everyone know what I mean by that? So if I was using this model to predict at, say, temperature of 300, I would say it is this plus this number divided by 300 plus this number divided by 300 cubed plus this number divided by 300 to the 6th plus this number divided by 300 to the 9th. How do you know that this last one had to be on the x to the -9 term? In case you forget the order. What would happen if I did this term as my x to the -9? And I did this divided by 300 to the 9th. It's basically, it doesn't take in, it's negligible. Right? It doesn't come into account in the model anymore. Anyway, so this is x to the 0, x to the -1, x to the -3, and so on and so forth. And what specified that? It is the order that I made my array. The first column was x to the 0, next one was 1 over x, 1 over x cubed, and so on. So you have this tool to use in anything, quizzes, analysis, homework, and I just want you to know how to use it. What do the inside bands mean? What do the outside bands mean? How do I use it to get my confidence interval and my slope and my intercept?